All right, y'all. So in this video, we are going to learn about a topic called moles. So the mole, which we abbreviate as MOL, yes, really, is the SI unit for the amount of substance, the amount of stuff. The number of particles, the number of things in 1 mole of a pure substance has been experimentally determined in a number of ways, and it's known as Avogadro's number. So, Avogadro's number is equal to 1 mole is equal to 6.022 times 10 to the 23rd, or if you're typing it into your calculator, 6.022 E23. So this can be a little bit difficult to grasp, but mole is just a word that means a number. So if we're talking about cookies in a dozen, 1 dozen means 12 cookies, 12 things. 1 pair is 2 things. 1 decade is 10 things. 1 mole is 6.022 times 10 to the 23rd things. It's just a word that means a number, but the number is really, really, really big. So, as we are going into how to use this knowledge of a mole, keep in mind that if you can write something as a statement of equality, you can use it as a conversion factor. So the types of things that we know in moles, the types of things we can count, are ions, atoms, and molecules. But you can count lots of stuff. You can count puppies, you can count books, you can count protons. And if you can count it, you can group it into moles. So the last thing we need to remember before we dive right in is dimensional analysis. So remember, those steps are: number 1, start with what you know. Number 2, multiply by a fraction. Step 3, what goes up must come down. So we're going to keep following these exact same steps. It's just that now we know some new statements of equality. So number 1, how many moles are there in 6.53 times 10 to the 24th atoms of gold? AU is the atomic symbol for gold. So we're going to follow our same steps as always. Step number 1, start with what you know. 6.53 times 10 to the 24th atoms of gold. Step 2, times a fraction. Step 3, what goes up, atoms of gold, must come down. Now from here, we have to decide what goes on top. The only relationship that we know about atoms is how to get between atoms and moles. This is the relationship that we just learned. Atoms are a particle. They are a thing that can be counted. So they fall under this heading of 6.022 times 10 to the 23rd atoms of gold is equal to 1 mole of gold. So we'll plug in that relationship. 1 mole, 6.022 times 10 to the 23rd atoms. And now atoms of gold cancel out and go away. If we plug in right now, we will be left with moles of gold. And that's exactly what we were asked to find. So it's time to put this in the calculator. 6.53 E24 divided by 6.022 E23 is going to give us 10.8435736 moles of gold. And now our very last step, always, is to look at our sig figs. We started this problem with 1, 2, 3 significant figures. We multiplied by a conversion factor, which, remember, your conversion factors are never ever going to affect your sig figs. So the only number of sig figs in this whole entire problem that actually matter is these 3 right here. So we started with 3, we should end with 3. And our answer is going to round to 10.8 moles of gold, which is the same exact amount of stuff as 6.53 times 10 to the 24th, but it's just a lot easier to talk about when it's grouped into 10.8 moles instead of this many individual atoms. Really, it's just a matter of convenience. Number 2. This time we're going the other direction. We start with moles, we are ending with atoms. So step number 1, start with what you know. 3.4 moles of copper. Step number 2, times a fraction. Step number 3, what goes up, in this case moles of copper, must come down. Now, when moles are on the bottom of a fraction, we will eventually have lots of different options for what to put on top. For right now, the only thing we actually know about moles is how to go back and forth with atoms, so let's go ahead and put atoms on top. Because again, this relationship we just learned says that 1 mole of anything, copper, 1 mole of copper is equal to 6.022 times 10 to the 23rd individual things. So in this case, atoms of copper. So this relationship works with copper as well, and we can plug in 6.022 E23 for the number of atoms in 1 mole. And now moles are up, moles are down, moles cancel out and go away, and we'll be left with just atoms. So it's time to plug this into the calculator. 3.4 times 6.022 E23. Your calculator is going to give you 2.04748 times 10 to the 24th atoms of copper. Last step, just like always, check for your sig figs. We started with 2. This conversion factor is not going to affect anything, so we should end with 2 sig figs. So we should round this to just 2.0 times 10 to the 24th atoms of copper. A quick note that may have caught some of us by surprise on the test, maybe we forgot. You will always and forever have to show your work on free response questions. If it's a dimensional analysis problem with atoms and moles, if it's a simple subtraction problem, you're gonna have to show your work. No work, no credit. All right, so at the bottom of this page, you have a little bit of practice. Go ahead and pause the video, work these problems, check the key, and then move on. But get comfortable with what we've already learned before you start adding new stuff. Okay, so in the last section, we learned about Avogadro's number, which is how we go from moles to things, particles, atoms, molecules. Another way we can talk about moles is with molar mass. So molar mass is the mass of 1 mole of a pure substance. Molar mass is written in units of either G/mol or grams over moles. Regardless of which way it's written, it's generally written this way. Regardless of which way it's written, it's always read as grams per mole. Remember, per in math means divide, so grams divided by moles. Something you're going to notice about this when we start looking at molar masses is that the molar mass of an element is going to be numerically equivalent to the average atomic mass of that element. The number we're going to use for molar mass is the same number we were using for average atomic mass, but that doesn't mean they're the exact same thing. So average atomic mass, we learned on day 1 of the unit, the units are AMU, atomic mass units. And when you're talking about elements in terms of AMU, you're talking about the mass of 1 atom of that element. Versus molar mass, the units are grams per mole. When you're talking about the molar mass of an element, you're talking about the mass of an entire mole of atoms. So they're on completely different scales. Average atomic mass, 1 single atom. Molar mass, a mole of atoms, which sounds like a lot, but keeping in mind how tiny they are, a mole is actually kind of a manageable amount of stuff. So let's see some examples. Number 1, what is the mass of 1 mole of uranium? The atomic symbol for uranium is U. It's down at the bottom of your periodic table. Looks like this. It's number 92. And this number in the bottom is 238.03. Now on day 1 of this unit, we would have said that means the atomic mass of uranium is 238.03 AMU. And that's still true, but that's not what we're being asked to talk about here. Here we're not being asked to talk about 1 single atom. We are being asked to talk about an entire mole of atoms. So it's still gonna be 238.03, but since we're talking about a much larger scale, we would say this is grams per mole, or since we've already been told it's exactly 1 mole, just 238.03 grams. Scandium is number 21, atomic number Sc. Again, the decimal number at the bottom of the square. We could say that that means that the atomic mass is 44.96 AMU. A single atom of scandium has a mass of 44.96 AMU. But we can also say that an entire mole of scandium has a mass of 44.96 grams, or the molar mass of scandium is 44.96 grams per mole. Like we said, because this per means divide, because per in math means divide, molar mass is quite literally grams divided by moles. So we can also find molar mass by taking your number of grams, your mass, and dividing it by a number of moles. For example, a 2.000 mole sample of an element is measured to have a mass of 61.94 grams. We want to identify the element and state how we know. So we've learned a couple of different ways of identifying elements. We've learned that if we have a density to compare to, we can identify by density. We've learned that if we know the atomic number, we can look at the atomic number. But moving forward, another way that we can identify elements is with their molar mass, which is what we should do here, because we have a number of grams and we have a number of moles. So we should do grams divided by moles to find the molar mass, and then we can compare it to the molar masses in our table. So we'll do 61.94 over 2.000. Plugging that into the calculator, rounding it to 4 sig figs, we'll find 30.97 grams per mole. So now we just need to look at our periodic table, look at the things that have masses around 30.97. Remember, the molar mass is the decimal at the bottom, not the whole number at the top. We're not looking at these. We are looking at the masses down here. So the closest ones are aluminum, which is a little under 27, silicon, a little over 28, and phosphorus, which is on the nose, 30.97. It's the only one that's close. The next closest one is sulfur. It jumps up to 32. So that tells us that we must be looking at a sample of phosphorus because it has the exact same molar mass. So because molar mass can literally be written as 1 mole equals this number of grams, that means it can be written as a statement of equality. And if it can be written as a statement of equality, it can be used as a conversion factor. So we can use molar mass in our dimensional analysis as well. So number 1 says how many grams are in 2.00 moles of palladium? The atomic symbol for palladium is PD. So we'll start with what we know, 2.00 moles of palladium. Step 2, times a fraction. Step 3, what goes up? Moles of palladium must come down. And now we need to decide what goes on top. In the last section, we learned that we're allowed to put atoms on top. We know that relationship. But in this case, it's not actually helpful because we're not looking for atoms. We are looking for grams. And that is a relationship that we just learned. So we can go ahead and put grams on top. Because if we look at our periodic table, we can see from this number right here that the molar mass of palladium is 106.42 grams per mole. Put another way, 1 mole of palladium weighs exactly 106.42 grams. So that's our statement of equality. We can put those exact same values into a conversion factor. 1 mole, 106.42 grams. And now moles of palladium are up, moles of palladium come down. If we plug in right now, we will have units grams of palladium, which is what we are looking for. So it's time to multiply it through. 2 times 106.42 is going to give us initially 212.84 grams of palladium. But of course, just like always, our last step needs to be sig figs. So we started with 3. This is a conversion factor, so it's not going to affect our sig figs. So we started with 3, we should end with 3, and this is going to round up to 213 grams of palladium. Number 2 here has us going the other way. We start with grams and we end with moles. So we will start with what we know, those 78.2 grams of bismuth. The symbol for bismuth is Bi. So we'll start with what we know, multiply by a fraction. Grams of bismuth are up, grams of bismuth come down. When grams are in the bottom, we do not get to choose what goes on top. When grams are in the bottom, we are allowed to put exactly 1 unit on top, and it is moles of the exact same thing. Lucky for us, we do know this relationship between grams and moles. It comes from the periodic table. Looking at bismuth on the periodic table, we can see that the molar mass is 208.98 grams per mole. Put another way, 1 mole of bismuth has a mass of 208.98 grams. So we can fill that in our conversion factor. 208.98 grams in 1 mole. And now grams are up, grams come down, grams cancel out and go away. If we plug in right now, we will have moles of bismuth, which is what we are looking for. So let's go ahead and do that. 78.2 divided by 208.98 is going to give us initially 0.3741984. And now because we started with 3 significant figures, and because we multiplied by a conversion factor, which does not affect our sig figs, we should therefore end with 3 significant figures, and we should report our answer as 0.374 moles of bismuth. Okay, so we have learned how to go between moles and atoms, or really any kind of particle. We have learned how to go between moles and grams. There's one other way we can use these moles, and that is to go from moles of one thing to moles of a completely different substance. So things we can change between, we can change from moles of atoms to protons or neutrons or electrons. We know how these things relate to our total atoms. We spent most of our first day of the unit learning it. So, for example, number 1, how many moles of protons are in 1.17 moles of carbon-13? We're going to follow the same steps. Step number 1, start with what you know, which is 1.17 moles of carbon-13. Step number 2, times a fraction. Step number 3, what goes up, moles of carbon-13, must come down. Now, when moles are on the bottom, we get to choose what goes on top. We could put grams of carbon-13 up there if we were looking for mass. We could put atoms of carbon-13 up there if we were looking for individual particles. Or we can put moles of a completely different substance up there. And since we are asked to find something about protons in this problem, protons and carbon are not the same thing. This would be an excellent time to put moles of protons on top here. Probably feels weird, but we do know this relationship. If you look at carbon on your periodic table, we can see that carbon has an atomic number of 6, meaning every single carbon atom that has ever existed, that will ever exist, has exactly 6 protons. So, if one single atom of C13 has 6 protons, we can scale that up and say that 1 mole of C13 atoms contains 6 moles of protons. You can just insert that word mole right in the middle, and the relationship doesn't change. So this relationship is what we can plug into the problem. A single mole of C13 contains 6 moles of protons. So then moles of C13 are up, moles of C13 come down, moles of C13 cancel out and go away, and right now, if we plug in, we will be left with moles of protons. Sure enough, that's what we're looking for, so it's time to plug this into the calculator. 1.17 times 6 is going to give us 7.02. Now we check for sig figs. We started with 3 times a conversion factor. We should end with 3. And that's already how our answer is written. So this is our final answer. In 1.17 moles of carbon-13, there are 7.02 moles of protons. Let's take a look at number 2. How many moles of neutrons are in 2.36 moles of carbon-13? Same process as always. Step number 1, start with what you know, 2.36 moles of C13. Step 2, times a fraction. Step 3, moles of C13 are up, moles of C13 come down. Now once again, since moles are on the bottom, we get to choose what goes on top. We could put grams of carbon on top, we could put atoms of carbon on top, or we could put moles of a completely different substance on top. And since this particular problem is asking us to find moles of neutrons, that would be a very smart thing to put on top of this fraction. Because again, it may feel awkward, but we do know the relationship between carbon-13 and neutrons. Looking once again at our periodic table, carbon still has that atomic number of 6, meaning every single atom of carbon that has ever been, every single atom of carbon that will ever be, has 6 protons in it. Carbon-13 has a total mass of 13, meaning 13 things in its nucleus. If we take its protons and add those to its neutrons, there are 13 things total in that nucleus. So, if there are 13 things in the nucleus and 6 of them are protons, we can say that 13 minus 6 is 7. So in one carbon-13 atom, there are 7 neutrons. 6 protons, 7 neutrons add up to give us that mass of 13. And just like before, we can insert that word mole right here without changing the relationship. 1 mole of carbon-13 atoms is equal to 7 moles of neutrons. So that's the relationship we'll insert here. 1 mole of C13, 7 moles of neutrons. And now moles of carbon-13 are up, moles of carbon-13 come down. We are left with moles of neutrons, which is what we are looking for. So it's time to plug this into the calculator. 2.36 times 7 is going to give us 16.52 moles of neutrons. Once again, check your sig figs. Started with 3 times a conversion factor. We should end with 3. So our answer should round to 16.5 moles of neutrons.